So I'll go back to Introduction to Bode Plot. I want to show you the math behind what I said about the zeros on the poles. Again, Bode plot is really an approximation. It's not the real answer. It's an approximation to what the graph looks like. And what we graphing, you need a semi-log paper. I just don't have it. What you graphing on the y-axis here, if you were to graph it, versus the x-axis, is normally you graphing W here, and on the y-axis you're graphing 20 log the magnitude of the transfer function, whatever h of s is. Or a lot of times, since we're dealing with the frequency, we replace s with j omega, h of j omega. H of j omega. There we go. So for example, let's say I gave you the transfer function h of s equals, I don't know, s plus, somebody pick a number, any number you want to. 7, okay. David picked 7. First, I want to do what h of j omega, so you replace s with j omega, and that's j omega plus 7. I kind of like the j omega because my s's look like 5. So this way you know that's omega. Does it look focused? Mm-hmm. Yep. What is the magnitude of that? Usually, by the way, I take this one, the way I take this function, I say, you know what? I like that number to be 1. So to make it a 1, I can divide everything by 7. I go 7 times j omega over 7 plus 1. Notice if you multiply that, because I like that number being 1. So 7 times j omega over 7 is j omega. 7 times 1, that's the 7. So what's the magnitude of that? The magnitude is going to be 7 times. And when you have a complex number, what's the magnitude of a complex number? Isn't that the real value squared? The imaginary value squared, you take the square root of that. So the real value squared plus the imaginary value squared. The reason there's a 7 in the front, because of that 7. So that's 7 times, what is 1 squared? Is 1. When you square the imaginary value, that's w squared. We don't square the j, just the imaginary value. J means it's imaginary, over 49. Now, we're going to be plotting here 20 log of that. So we're going to plot 20 log of the magnitude, which is that value. You can also plot the phase there, but that's what you're going to be plotting there. Now here's what I want you to think about, what will happen in terms of math. Let me just... I'll save this paper. I'll use normal paper for now. What will happen if W is much, much smaller than 7, which is the square root of 49? I.e., example, what about if W equals like 0.1? What's going to happen to W squared over 49?
It's going to be a very small number.
Very small number, almost a 0. So the answer becomes approximately 20 log 7 times the square root of 1 plus 0, which is 20 log of 7. And if I get my calculator, that's approximately equal to what? (20 log of 7), which is 16.9 decibel. What about if W equals to 7? That means W squared would be 7. 7 squared is what? 49 over 49, that's a 1, right? So this will be, well, not approximately, it will be exactly here, 20 log 7 times the square root of 2. Seven times the square root of 2. Take the log of that times 20, which is 19.9, approximately 19.9. Notice this number is what? 3 decibels above that. Can you see that? And what about if W is much, much larger than 7? Now let's see, if W much, much larger than 7, you ignore the 1 in this expression, right? Because this number becomes way larger than 1, so it's not even worth adding. So approximately will be 20 log 7 times the square root of W squared over what? 49, which will give me approximately 20 log of 7 times W over 7. The 7s will cancel each other out. Would be 20 log of W. So what happens? Let's look at this now. If W becomes 10 times that number, so you're going to have what? 20 log of what? 10 times W. And if you know the rules of log is what? You can break it down to 20 log of 10 plus 20 log of what? W. What's 20 log of 10? Log of 10 is 1 times 20, that's 20 decibel, plus whatever the value used to be. Let's see what we're looking at. Let's say I want to graph that function, see what it looks like. On the x-axis, on W, I want to go a multiple of 10s. So let me start with the 0.1 here. What's 0.1 times 10? Is that a 1? What's 1 times 10? 10. What's 10 times 10? 100. What's 100 times 10? 1,000. I'm going by multiple of 10. You'll see why 10. And this is 0 decibel. 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, right? So if I graph that, when it's W equals 0.1, the value is almost 16.9. That's just a hair over 15, right here. If I did the 0, if I plugged in 0, guess what the answer is? Still 16.9, right? Because I ignored that. So it's really constant. So far, it's constant. When W is very small, that value is at about 16 some change. And it stays the same almost till W becomes what? 7, where's the 7? The 7 is right here. 1, 3, 6, 7 is right there. At 7 is going to go a little bit higher to about 19. And this one says if W becomes 10 times larger, when W is bigger than 7, start to rise, start to go up. So this one says when W becomes 10 times larger, that's what this one is, the value is going to be 20 more than that. So let's go 10 times more than 7. Where is that? 17? Right here. That's the 17. This is the 7. This is the 17. What's the value of W is going to be? It's going to be 20 more than what it used to be, right? 20 plus that number.
So it's supposed to be at 70? 70?
10 times, yeah, 70, thank you. 70, yep. 10 times that number. It's supposed to be 20 more than that. Let's go 20 up more than this. This is 20. Where's 20 more? 40 is right here. Is that this number here? So the graph approximately looks like this. It's going to go per decibel, increase at the rate. Notice the rate here, 20 decibel per decade. Decade means what, 10? Factor of 10? That's why here we went by factor of 10. For every 10, multiple of 10, it rises by 10 decibel. Well, the Bode plot says you don't have to pick all these points, but you can see it's going up. So the Bode plot says the way we're going to approximate this graph is by drawing a 0 till we hit the first 0, which is the 0 happens to be where? What value makes this one 0? Well, or 1 here. To be equal to that, that's a 7. So we're going to stay the same number till we hit 7. And once we hit 7, there's a 7 right here. Then we're going to go up here at the rate. And the drop between the real value and the blue line and the red line is the 3 decibels. Because I'm approximating that with a straight line. I'm saying it's not going to change till we hit 7. Then it's going to shoot up. And that gap right there, it's really 3 decibels. Because at t equals 7, the value was 19.9. Here I'm approximating that with what? 16 some change, 16.9. So that's why the Bode plot says when you see a 0, you go up by 20 decibels. When you see a pole, you come down by 20 decibels. Let me prove the pole to you. So let me take an example and do poles in it. Somebody pick a number. Again, any number you want to.
15.
15. So h of s equals 15 over s plus 15. Again, I want to do the Bode plot for that. We have a pole now because we have a value in the bottom that will make it 0. That's called a pole. So So first, I want to make sure I change it to h of jw because we're plotting a frequency. That's 15 over jw plus 15. I like that number to be 1. To make that number 1, I'm going to divide everything by 15 here. This will be 15 times jw over 15 plus the 1. You agree with that? What's 15 over 15? 1 over 1 plus jw over 15. So what is the magnitude of that? The magnitude. Oh, here we go. It is the magnitude of the top, which is 1, over the magnitude of the bottom, which is the square root of 1 plus w squared. What's 15 squared? Is that 225? So again, when w is much, much smaller than 15, and you can use any number you want to, i.e., let's say w equals, I don't know, 0.01. It's much smaller. This term will go to 0. So you're going to end up with the value approximately plotting 20 log. 20 log of 1 over the square root of 1 plus 0. That's a 1. 20 log of 1. We know log of 1 is 0 times 20. That's approximately 0. Let's see what's going to happen when w equals to 15. This will be what? 20 log 1 over the square root of 1 plus 1. Log 1 over the square root of 2. Let's see what that answer is. 20 log, where's the log function? Parentheses 1 divided by the square root of 2. It's -3. Interesting. Decibels. Notice at that value, it's always 3 decibels below that. 3 decibels below that. Always. You saw that in the previous example. So what about if w is much, much bigger than 15, like 1,000? Let's say w equals 1,000. I mean a big value. When you square that, that term is going to be much bigger. This one is going to be much bigger than the 1. So you're going to have approximately 20 log of 1 divided by, what is the square root of w squared over 225? Isn't that w over 15? Because that would be way bigger than the 1. The 1 is not worth adding, which is 20 log 15 over w. And whatever that number is. Now just think about this. W is a big number, right? If w is a big number, this value is less than 1. What do we know about the value of that number? It will be negative. So all I know, it's a negative value. But now what will happen if W somehow becomes 10 times that value?
Well, the same thing that happened before.
Except when you look at this, I should have did one step before I did this, before I said if W, because I could have simplified this, right?
You want to split it?
I'm going to split it down to subtraction, right? So this will be, before I do that, makes the math easier, 20 log what? 15 minus 20 log W, right? Now, if W becomes 10 times W, this is going to change. It becomes 20 log of 15 minus 20 log of 10W. 20 log of 15 minus 20 log of 10 minus 20 log of W.
Plus between those?
Well, minus a minus, right?
Oh,
Because that's a plus with the minus makes it a minus. So it becomes 20 log of 15 minus 20 log of W. And what is log of 10? 1 times 20, that's negative 20. And if you look at it, it says, wait a minute. See this value? That's this piece. What happens as you increase the value by 10 times? The Y value drops by what? 20 decibel per decade. That's why the poles pull you down by 20 decibel per decade, where the zeros pull you up. I just want to show you the math behind them. So if I was graphing this function, if I was to graph that, this is W. Again, this is 20 log absolute value, which is the magnitude of H of JW. So again, I can start with 0.01. 10 times that, 0.1. 10 times that is 1. 10 times that is 10. 100. 1,000. 10,000, so forth, you know. When W is very small, we said very small, what's the value? 0. I'm going to make this 0 decibel. I'm not going to put it on this axis. This is negative 20. This is 20 decibels, and so forth. So it's going to start 0 till we hit the pole, which happens to be where? At 15, right? So at 15, 15 is somewhere here. This is the 15. Somewhere here is the 15. This is the 15. So it's going to be 0 decibels. So the Bode plot says, don't worry about dropping that 3 decibels. It's going to be 0 up to this point. And once you hit that pole, what's going to happen? It's going to decrease at the rate of what? 20 decibel per decade. What's 15 times 10? It's 150, which is right here. This is the 150. So by the time it goes from here to here, it should drop by 20 decibel. If you're 0 here, 20 decibel puts you right here. See that? Negative 20 decibels. So the graph will be this way. Negative 20 decibel per decade.
so when we have the Laplace function, we can graph that in terms of decibels and frequency.
Yep, that's a common graph. The reason what they like about this is if you have this graph, you can always go to the transfer function too.
You can
You'll
go
see.
into like voltage.
Yep, I can, well, this could be a voltage gain, could be a current gain, could be V out over IS, you know, could be anything. If you were to do the actual graph, David, this will be actually 3 decibels below that. So you just saw that because we just calculated the math for it. When it's 15, oh, where was it? Oh, right here. When it's 15, it was a -3, right?
Oh.
See that? So technically, if you were to graph the point by point, if you go to Mathematica or MATLAB and you graph it, the graph will not look like this, it will look like this.
But it's the graph in Laplace way.
Yep, I'm graphing the transfer function. Yep. Yeah. And that'll be actually a graph if you were to graph it in versus the frequency, not Laplace. If you graph this just with the 20 log of h of j w versus w, so you graphing with respect to the frequency. What happens as the frequency increases? That's what your function looks like. And the drop here, the drop is 3 decibels. You know, so the red one is really what the actual graph will look like, and that's the approximation, the Bode plot. So instead of actually deriving that every time you have a 0, it's going to go up by 20. Every time you have a pole, a 0 will go up by 20 decibels. A pole will pull you down by negative 20 decibels. I'm just going to use that from now on. I'm not going to go if W is less than this, if W is bigger than that. I'm going to find out where the zeros and poles. And if you look at mathematically here, the 0 was at s equals to 7, right? What value makes this one 0 technically? You know? When we did this one, where'd you go? There we go. Where's the value? It's at 15, right? That's where it happens. At t equals 15, that's when it goes down. You have a pole, it's in the bottom. It's going to come down at 20 decibels per decade. So let's do one without having to spend 6 hours on it. I wasn't expecting to find my book today, so I brought my book. But let me take one. H of s equals I can make it a bigger problem. 50s squared plus 110,000 s plus 20 million. Over s squared plus 20,000 20s plus 400,000. You can factor a 50 out and factor the top and the bottom, and here's the good news. If you factor the 50 out and you factor the remainder, the top and the bottom, if I did it right, I cheated. I went to Mathematica. And the bottom, s plus 20, s plus 20,000. I can make any problem work. You know how? You work it backward. You choose what you want to have for numbers on the bottom. Notice if I want the numbers in the bottom to be different, if I want 50, 75, 40, and 30, I go s plus 50, s plus 75, s plus 40, s plus 30, and you fold them out, right? So really you choose your answer, then you work the problem backward. We make these problems, that's what we do. We decide where we want to have our poles and zeros, FOIL it out, multiply, oh, let's multiply this by 7 just to make it more fun. And you end up with some crazy question. But it looks like, wow, what a brilliant person came from this to this. No, we work it backward. We choose what one for the answer to be, FOIL it out, and you end up with that problem. So don't be impressed, you know, that, wow, we can get the answer quickly, you know. Now, I need to convert this to JW. Because we're plotting frequency. There's no S in our lab or anything. So let's be 50 JW plus 200 JW plus 2000 JW plus 20 JW plus 20,000. I know my zeros and poles, but I'm going to go through the math just to make everyone happy who's watching the video. But I know the zeros is going to be at 200, at 2,000. The pole is going to be at 20 and 20,000. But what we're supposed to do to make the circuit people happy is divide, make sure this number is 1, this number is 1, this number is 1. If we do that, and the way you can do it, there's the 50 sitting in the front. To make that a 1, you want to go JW divided by 200 plus 1, and you multiply that by 200. And to make that a 1 here, times 2,000 JW over 2,000 plus the 1. The bottom, I want that to be a 1, so it's 20 times JW over 20 plus 1. I want that to be a 1, 20,000 JW over 20,000 plus the 1. And these numbers, if you play with them, 20, that's a 10, you know what? This, and this. If you multiply them, they cancel each other out. See that? This is a multiple of 10, and that's a multiple of 10. So they do cancel each other. You end up with 50, 1 plus JW over 200 times 1 plus JW over 2,000. 1 plus JW over 20, 1 plus JW over 200,000. Or 20,000, not 200,000. That's 20, right? The last one?
20,000.
Yep. So I know where my poles and zeros are. These are the critical values. 200, 2,000. These are the zeros. 200 and 2,000. The poles are the bottom. What are the poles? At 20 and what? 20,000? Now, first thing first. When W is very small, because we have to have a value there, like 0. I'm going to have what? 20 log the magnitude, which is what? 50. Approximately, that's 34 decibels. This is 0, 0, 0, 0. That's 1, 1, 1, 1. 20 log of 50. So when I graph my function, I'm ready to graph it. Let's mark the zeros. Should we use maybe a blue color for the zeros? So let's begin. This is 0.1 or 0.01.
We start with 0.02.
What'd you say?
I guess we should start with 0.02.
Yeah, 0.02 multiple. It looks like everything is a multiple of what? 20. So 0.02. What's the next one? 1, 2, 3, 4. Times 10, 0.2. Times 10, 1, 2, 3, 4. That's 2, right? Times 10, 1, 2, 3, 4. 20. Times 2, 1, 2, 3, 4. 200. 1, 2, 3, 4. 2,000. 1, 2, 3, 4. 20,000. 1, 2, 3, 4. 200,000. I'll use blue for the zeros. We have a zeros where? At 200. See the blue color? Can you see blue? And at 2,000. Right? We have a pole where? I'll use red for the pole. At 20 and at 20,000. Now, the initial value, which is a 0, 34. Five, 10, 15, 20, 25, 30, 35, 40. Let's do by 5. 5, 10, 15, 20 decibels. 25, 30, 35, 40. 45, 50, 55, 60 dB. So this is 20 log H of J W. And that's your W here. We're going to start at 0 with the value of 34 roughly. 34. Where's the 34? 20, 30, 20, 25, 30, 35. Just a hair below the 35, right? And it's going to stay till we hit the first pole. This is the pole. Let me just mark it. I don't need this sheet now. This is the pole. I'm going to draw lines up and down so I know where they are. I should make the poles in red. So these are the poles in red, right? And I'm going to make the zeros in blue. The zero is going to pull me up at the rate of 20 decibels per decade. So these are my poles. And the blues are my zeros. And let's see. I'm going to have a value of 34, and it's going to stay the same till I hit the first pole. Just a hair below 35. Once I hit that, it's going to drop by 20 decibel by the time I go from here to there. 20 decibel is going to put me right here. Negative 20 decibels. Now what's going to happen here, I'm going to hit a 0. A 0 is going to pull me up by 20 decibel. Well, if I'm going down by 20 and you start pulling up by 20, what's going to happen? It's going to level, right? Because what you're looking at quickly is just, this is like going like this. I'll put color lines like this, see it? And you have a 0 pulling up at 20 decibels like that. So what's the net result of these two? It's going to be a straight line. Till we get to this point. Now what happens here? We encounter another 0. It's going to pull up at the rate of what? 20 decibels. So you're going to go up here at the rate of 20 decibels. And this wants to continue. But what happens, we get a pull now, it's going to pull you down here at that rate, and these two will cancel each other out. You end up with what? Another straight line. And that's the Bode plot for it. Again, this is the approximation where if I graph the 20 log, the real graph, instead of the Bode plot, the graph will look like this. Dips down a little bit here. That's what the graph will look like. Each corner is a drop 3 dB. You know? But quickly, boom, I have the answer. The nice thing about the Bode plot, if I give you the Bode plot and I give you a value here, what was it, 34 we said here? 34 at this number, you can work the problem backward and get what the function is. So let me take a problem from the book and see if I can give you the Bode plot and work it backward. And that's really what makes the Bode plot attractive, is the capability, if you have the Bode plot, is to get the function. Where'd you go? Where'd you go? Okay. They use actually MATLAB in our book a lot instead of Mathematica. I'm going to go to MATLAB, I think, next year. Where'd we go? I can't find it, but I'll make one up. I'm looking in the book and I can't find one, so I'll make one up. I don't know what chapters they're in. So let's say, here we go, this is 0.05. Uh-oh, I didn't mean to make it continuous. I want a dotted line. Point 5, 5, 50, 500, I don't know. Let's say I was coming down at the rate of negative 20 decibels. Negative 20 decibels. Then it leveled here. Then it went up at 20 decibels. Now let's say now went up to plus 40. So this is now plus 40 instead of 20, twice that. Then plus 20, I'm out of space there. And let's say it leveled here. Given that function, I decide to,
Value?
huh?
Do we have an initial value?
Initial value? I'm going to give you one. Pick a value. What do you want to use? 0.1, 0.01, whatever you want to. You want 0.1 here?
And then
And let's get this value to be, pick a number here. Anything you want to, in decibel.
40.
40? Okay, dB. So what is h of JW? Some constant, I need to find what that constant, I'll get that later. Might be a number in the front. That's where the significance of this value, 0.1, comes in. It looks like I started with a pole down, right?
Yeah.
That means I have a JW in the bottom, a 0. And what happens at 0.05? It leveled down, right? So a level, that means what? Something was pulling up. There's a 0 there. That's why it leveled. Somebody was pulling up at 20 dB. So I got JW over 0.05 plus the 1. Then I went up at the 20 decibels here, where? At 0.5. That means there was another 0 pulling up. See, there's a 0 pulling up. That's a JW at 0.5 plus 1. We have another one, another 0, because it's continued to go up at the rate of 40. That's JW over 5 plus 1. Now, instead of going to plus 40, decide to go back to plus 20. Plus 20, that means what? Something pulled it down here by 20 decibel. That must be a pole in the bottom. JW over 50 plus 1. And the factor level, that says there's another one where? JW over 500 plus the 1. Now, I don't like the way that looks there. Maybe I can clean it, get rid of all these little fractions. I'm going to multiply both these by 0.05. I forgot to write the .05 in the front. Give me some room here. This one I gotta multiply by 0.5. This one by 5. Yeah, I gotta divide them. Let's see. That means I gotta divide this what by what? 0.05? 0.5 and the 5. You can't just multiply by 0.5 on the top and not multiply the bottom. Oh, you know what? Yeah, I don't need the 0.05 on the top here. I already took care of that. I multiply the top and the bottom, but here we go. Let me just slowly here. It looks ugly. I'm going to multiply the top and the bottom by 0.05. I try to rush through it. JW over 0.05. I'll come back and multiply it. That means I need 0.05 in the bottom. I got to multiply this by 0.5. And if I multiply the top by 0.5, I'm going to multiply the bottom by 0.5. Let me multiply this by 5. If I multiply the top by 5, I'm going to multiply the bottom by 5. Now let's deal with the bottom. With the JW. Let me multiply this by 50. That means I got to multiply the top by 50. And let me multiply this by 500, right? That's the math. Multiply the top and the bottom by these numbers. Now we try to clean it. Okay. Let me just see what these numbers are equal to. $500 times. I'm going to leave the 0.05 out there. I'm not multiplying by the 0.05 because I'm going to distribute the 0.05 in a minute there. So 500 times the 50 divided by 0.05 divided by 0.5 divided by 5, 200,000 K. $200,000 Now let's multiply that number. Let's see what happened the rest of it. What's 0.05 times this? That's canceled. That's 0.05 plus JW. What's 0.5 times that? That's 0.5 plus JW. That's what? 5 plus JW. All divided by what? JW. 50 plus JW. 500 plus JW.
5 plus JW meant 50 plus JW?
50 plus KW up in the bottom.
So, that number 200K, was that from multiplying the
That's actually, the K is the constant in the front, which we're not sure what that number is, right? So it's 50 times 500. I don't multiply this, no.
I think it's 25,000.
50 times 5, then you got to divide it by these three numbers.
Divided by
Already
the.
do
Yep.
that? Oh, okay.
Yeah. So that's what you have. Now the magnitude of that, because you don't find what K is going to be 200,000 K. The magnitude of this, which is the square root of what? 0.05 squared plus W squared, times the magnitude of this, which is 0.5 squared plus W squared, times the magnitude of this, which is 25 or 0.5 or 5. That's not a 0.5, that's a 5. Five squared plus W squared, all divided by the square root of W squared, right, which is W, the square root of 50 squared plus W squared, the square root of 500 plus W squared. Now I gave you a value on the graph for W equals what, 0.1? So now let 20 at W equals 0.1, it was 40 decibels, right? So that means 40 equals 20 log 200,000 K. Now plug in 0.1. When you square it, 0.01. What's 0.05 squared plus 0.1 squared equals, take the square root of that number, 0.118. What's 0.5 squared plus 0.01 squared? Take the square root of that number, 0.5. What's 5 squared plus 0.01 squared? That becomes silly to add the 0.01, right? Take the square root of that number. That's a 5. That's a W, which is 0.01. That's a 50. And that's a 500. Forty divided by 20 is what, 2? So let's take these numbers and see what is 200,000 times 0.118 times 0.5 times the 5 divided by 0.01 divided by 50 divided by 500. Log 236 times K. 236K equals 100, right? 10 squared, which is 100. K equals 0.424. Now you know what the answer is. Plug it in here, right? Go into times the 200,000. So if you want it as a function of S, you replace JW with S. H of S equals 200 times K, which happens to be 84745, times S plus 0.05, S plus 0.5, S plus 5, over S times S plus 50, S plus 500. And we get our transfer function. That's it.